Hello there, I hope you're doing well. Now, welcome to our today's practical session. And today we are doing, this is Physics 0625, and that is May-June, variant 51, 2017. You can always go and confirm. So, my very first statement, if you've been watching my videos, then you know the very first thing to do is to go through the paper together to be able to understand what the question wants you to do. So the very first thing is in this experiment, you will investigate the stretching of a spring. Carry out the following instructions referring to figure 1.1. So on that figure, you can able to see there is a complete stand there. There's a spring hanging on the stand. Then there's a meter rule. Of course, the meter cannot stand alone like that. That means there must be a stand, as you can able to see, that is supporting the meter rule. Part A, do not remove the spring from the clamp. Use the meter rule to measure the length L0 of the coiled part of the spring. Record L0 in the table 1.1 at the load 0.0 newtons. On the figure 1.1, show clearly the length L0, that is on the figure. Part B, place a load L is equal to 1.0 Newton on the spring. Record in table 1.1 the length L of the coil part of the spring. So this is very, very clear. They ask you the coil part of the spring. Sometimes it can be like the length of the entire spring, but this is only the coil part of the spring. The next part is that repeat these procedures for the loads 2 Newton, 3, 4, and 5 Newtons, and then we record them in the table 1.1. Part C, describe one precaution that you took in order to obtain reliable readings. So I need to know which kind of precautions I need to do when I'm doing this kind of experiment, and we'll try to see if you can able to do that. Then part D, plot a graph of L in millimeters against the load in the x-axis. Part E, a student suggests that length L of the spring is directly proportional to the load L. State whether your readings support this suggestion. Justify your answer by reference to the graph line. That means we have to plot the graph first. And then part F, use your results to predict the load L that will give a length twice the value of L0. Show clearly how you obtain your answer. So it is always good to read through the question, and the main reason is this, as sometimes maybe there can be a question that still requires to take some reading, but if let's say you have dismantled your setup, it will be a time wasted. So always go through the question so that you know, at least you understand which part you just need to do the experiment, and then you can be able to sit down and do the analysis. So without wasting time, let's start doing what the question instructs us to do. So this is 1.8 centimeter. So the length, as you can able to see, at this particular point is that is 49.7 mark, and then the lowest part is 51.5. So that means the length of the coil part is 51.5 minus 49.7, which gives us 1.8 centimeter. But then now, because our data, the table here is in millimeters, so that will be, we multiply by 10, so that will be 18 millimeters. So this is just 52.8. So for us to find the extension, that will be, so 52.8 minus the initial one, that was 49.7. That should give us 3.1. So that is 3.1 centimeter. And we do that, that will be 31 millimeters. So we're going to repeat that experiment the way we have shown. Then you hang it slowly to minimize the deformation. I add the last one, so 5.0 newtons. You hang it slowly, you support, don't just leave it to fall down. So slowly you support it until that particular point. Try to avoid the oscillation up and down. When the mass is very heavy like this, it may deform. 58.9 minus 49.7, that is 9.2, which is 92 millimeters. So before we draw the graph, there is a question here. Describe one precaution that you took in order to obtain the reliable results. Reliable results is a result that even if you repeat under the certain conditions, you should be able to get the results that we just got here. So one of the things that you can do, and I think you saw me doing that the first, you can able to see what I did, is to use a set square. Use a set square. A set square. And the reason why I use the set square is to line up with the scale that I was using. Or you can also do another thing that I did was to do a perpendicular viewing, and you realize that my spring, the spring was close enough to the meter rule, so that increases the reliability of the results. All right, so let's look at our graph so that we can able to do the analysis. Okay, good. So plot a graph of L, that is a millimeter, and then against L in newtons. So the very first thing that I want to do before I even record anything is just to label my graph. So here I should be having length, which is in millimeter, and then here I should have load, which is in newtons. So the first thing to do is to label the axis before doing anything, because there is a mark there that I don't want to forget to lose. The next thing is to choose the scale that is suitable. So remember, the graph should cover at least 3/4 of this page that you have been given, the page of the graph. So that is our intention. So let's understand the scale that we're going to use in the x-axis. So in the x-axis, the lowest value of the load is 0 and the highest value is 5. So we just want to see if we can able to choose something that suits that. So let's say if we decide to choose, let's say these 10 small boxes or one big unit represent 1 unit. So this will be 1, 2, 3, 4, 5. 5 will be there, more or less almost 3/4. What if I decide to do this? Let's say the 2 big square represent 1 unit, 2, 3, 4. So if I do that, it won't fit. So that means the one that I have will be this. So I will start here at 0. That is on the load side. Then the other side, we have the lowest value on the length side, that is 18. The highest value is 92. So we want to look at the scale that we can able to use. So if we decide, let's say that this big box here, that is the 10 small boxes, each of them represent, let's say 10, then let's see how it will go. So this is 10. So 1, 2, 3, 4, 5, 6, 7. So it will be 70. So that will not work very well for us. So that means if we try 10 to be for the small, so this will be 10. This. So that scale is better. So 10, if we used 2, it was going to be more than that, but then now this will give us. The other thing is to understand what each small box represent so that we can able to do the plotting correctly. So along the y-axis, where we have the length, we have 1, 2, 3, 4, 5. So 5. So 5 small boxes represent 10 units or 10 millimeters. So 5, that is 10. What about 1 each small box? That will be 10 divided by 5, and that will be 2. It means that each small box along the y-axis represent 2 millimeters. 2 millimeters. We also need to understand along the x-axis what each small box represents. But then that is not a problem, because now on along the x-axis we have full units. So there's nothing like point something. So that will be very direct. So let's start plotting and then we see. So this is what I'm going to do. So when L is 0.0, of course this one here could also start from 0.0. Yes. So when the load is 0.0, when there is no load on the spring, you can see clearly this is 18. So what is 18? So this is 10. Let me magnify so that you see. Good. All right, so this is 10, means that this is 12, 14, 16, 18. So 18 is here. So the first point is here. Okay. All right, so we proceed. 1 and 31. So 1 and 31. 31 must be here, in the middle there. Okay. Another one is 2, 45, 2, 45, 2 and 45. Always use a ruler if you cannot figure out. So 4, that is 4 is along here to become easier. 70. So we talk about 76. So that will be our graph looks linear, which is very nice. But then sometimes your graph, when you're supposed to draw a line of best fit, you don't know whether the graph is a straight line or a curve. I will always ask you that before you draw your graph, you may think there's supposed to be a line of best fit. A line of best fit can be a curve or a straight line. So always check the next question. This question here, sometimes if you see a question here, the next after the graph, maybe they ask you to find the gradient. Find the gradient of the graph, then you know automatically that graph must be a straight line. But if they ask you to find, let's say, what is the value of L, when maybe this L is this value, that can be 50-50. Depending on your points, it can either be a straight line or a curve. All right, so for this, I will draw a line of best fit since my points seems to be linear. That is what I have. All right, let's see. Question number part E. A student suggests that the length L of the spring is directly proportional to L. State whether your reading support this suggestion. Justify your answer by reference to the graph line. So for L to be directly proportional to this capital L here, number one, it must pass through the origin. Number two, it must be a straight line. So it is a straight line, that's correct, but it doesn't pass through the origin. So no. So we want to say that no. L is not directly proportional to L since the line does not pass through the origin. Does not pass through the origin. So that is the mark that we can able to use there. So for that to happen, there are always two conditions. Part F, use your results to predict the load L that will give a length L twice to the L naught. So L naught, we got L naught to be, that was 18, of course, 18 millimeters. So 18 millimeters, so we take 18 times 2, that will give us 36. So we come here and read the value of 36. 36 is here, so this is 30, 2, 4, 6. So 36 is here. For you to show, you must show your work clearly. So that means there must be an evidence on the graph. There must be an evidence, and this is how you get the evidence. You come and draw here. You can point, well and good. So it is pointing almost in between. So this is 1, this is 1.1, 0.2, 0.3, but because slightly that, this can be 1.35, 1.35 approximating. So 1.35, 1.35. Forgot, that is Newton, and that is the end of this question. So